So hi everyone, Igor Oreper. I'm with Bitmovin. I want to maybe start with that question, and I'll dive into it a little bit here as well. I'm really focused on VOD encoding for VVC, and so I'll talk a little bit about where we are with VOD encoding in general, not just at Bitmovin, but also the market at large, and some initial deployment data. But I'll start with the Bitmovin Video Developer Report. So for folks who are familiar, this is a report that we do every single year. This was our sixth installment, published back in December of last year. And we surveyed over 400 respondents across the world about a bunch of different topics related to video streaming. And one of them was codec adoption. And so, the way we look at codec adoption, so we, among other things, we provide a software-based VOD encoder that runs in the cloud. And, we look at it as it's a tool set for developers to build video streaming services. And so in that tool set, you need lots of different tools, and codecs with various features are some of those tools. And so we always ask, what do you deploy today? What are you going to deploy in the coming 1 to 2 years? And you'll see here, of course, a lot of AVC adoption. This is very similar to the chart that Jan just showed, where you see kind of AVC over time going down, and you see other codecs over time coming up. I do think that there isn't a best codec. I think we are in a multi-codec world already, with a lot of publishers who have already deployed and run in production at least 2 or 3, sometimes 4 different codecs. And it really, each of those codecs targets different devices and device categories. Now you have a lot more flexibility in doing that kind of device targeting and transcoding to different output codecs because you want to get to the best efficiency with the best quality, exactly to solve the problem you're talking about, right? Cost for operating your streaming service, storage, data egress from cloud, CDN distribution, right? All of those things have a pretty big cost if you're talking about operating streaming service. And so from that perspective, here you see 15% of the respondents are saying, okay, we've already deployed VVC in production. Most of those are in Asia Pacific region, and I'll talk about why in a little bit. And then I think it's 29% are planning to deploy. And so all these numbers sort of change and fluctuate over time, but the reality is, VVC, HEVC, AV1, all of these are coming up. AVC deployment's coming down, but it's always a good fallback. So, I think, to Jan's point, folks will deploy the codecs that they know consumers can actually decode, whether software or hardware, ideally hardware, and adoption is really going to be driven by that. So I wanted to talk about some of the highlights. As Alan said, it's an evolution, not a revolution. Promised that these words were on here before he said them, but I did underline them after he said that. But it is versatile. And the second point is, I think, the biggest differentiator for VVC as a feature. There's lots of words you can use to describe it, but it's basically open GOP. It allows you to adjust bit rate over the course of the asset. And this is a really unique feature. I think RPR is what Alan referred to it as, because you get to reference previous frames in that asset, which allows you to make really smart adjustments to resolution within the title itself. So I think that's a really big differentiator, and it improves efficiency anywhere from 5 to 20%. So I just said 10% on average. There are also a lot of features that are built into the codec. So, it makes it easier to implement HDR and white color gamut, film grain synthesis, which Alan talked about as well, UHD 8K, right, immersive video. Lots of really good features that video engineers love. And all of that is built into the codec itself. I thought this was an interesting highlight from ByteDance, who have shared some results from their VVC encoder. They're seeing 53% bitrate savings compared to HEVC and a 10% improvement in speed, which I think is pretty cool. We haven't got there yet at Bitmovin, but we've only recently started investing in research and development there. And then when you compare it to the HEVC reference encoder, it's a 4% or so bitrate savings, but much, much faster, which is expected. So I wanted to talk a little, and this is specifically VOD encoding. In some cases, there are providers like Atem who provide both live and VOD, and then others who are live only. But anyway, open source. So the VVC test model is a reference encoder software that it's a decoder software as well, but I'll focus on encoding in this talk. And so this reference encoder just allows anyone who's implementing the codec to experiment with the features, experiment with performance. So Bitmovin has done quite a lot of work with the reference encoder. Fraunhofer, so they created VVC, VVEnc, which we talked about a little earlier. And I would say that's a real world encoder. There's also a decoder as well, and the latest version 1.8.0, it's all open source. Look it up on GitHub if you're interested. But it's the implementation that at Bitmovin we're currently collaborating with Fraunhofer very closely and building our optimizations on top of that. And then another German university that's doing a lot of research here, they built a bitstream analyzer, which is an add-on to the VTM decoder, super helpful to understand the bitstream itself. And so those are some open source projects that I think are noteworthy. And then there are commercial implementations as well. So Main Concept releases SDKs and plugins for VVC encoding, also including for live. The VVC encoder from ByteDance, for folks who may be not familiar, ByteDance is the parent company of TikTok. TikTok and many other applications are owned by ByteDance, and so they've got a lot of interest in compression just because of the sheer volume of content that they serve. And so their encoder, I think, is pretty well optimized, lots of features implemented, and as far as I know, it's a proprietary implementation. They're not using someone else's library. Tencent released RT1 in Tencent Cloud. This is a big cloud provider in Asia, specifically in China. Same for Alibaba, Ali 266 encoder in Alibaba Cloud, also big in Asia. And then Atem Titan, which Jan will talk about a little bit more. And I guess live is really the big focus there. And then Bitmovin VOD encoder, so I'll talk a little bit more about it, but basically it's a cloud native and agnostic cloud-based encoder, and we've integrated VVEnc. Currently it's internal, so it's not publicly available, but that's something we're working on. And then streaming services, MX Player, Jan mentioned a little earlier, they deployed VVC to 20% of their customer base in India, which is not insignificant. And one, I guess, a theme here to notice is a lot of service providers in the Asia Pacific region are deploying VVC. They were also first to deploy AV1 some years back, and they think a big reason for that is because of the many bandwidth constraints that exist in that region. Most folks are on cellular networks with very limited bandwidth, and so advanced codecs like VVC and AV1 play a really big part and offer a lot of value there. Okay, so a little bit more about Bitmovin's integration. So close collaboration with Fraunhofer. As said, we have a team of codec engineers in Berlin, co-located with Fraunhofer, and so we do a lot of research together. We did experiment with the VTM reference code base early on and got some really good results. We've now integrated VV-Inc, the open source project, into our software-based encoder, and also VV-Deck for playback in our player. We made contributions back to the project, mostly focused on the interface, so interface to the core encoder, and we hope others can benefit from that. It's all C code for anyone interested. So what we've seen so far is about a 40% BD rate gain compared to HEVC, and for some subjective tests, we see it as high as 50%. So I think that's pretty cool. In terms of compute, so again, we're a CPU software-only encoder, and so compute we measure in terms of CPU cycles. And so we see that it's about, we need about 8 times more compute when comparing to AVC, about 4 times more when comparing to HEVC, and 2 times more for AV1. I mentioned earlier the VVC encoder from ByteDance, they're 10% faster than HEVC. So, you know, they're basically 1x HEVC, which I think is pretty impressive. And so, what are we doing next? We want to get to 1x, so about on par with HEVC in terms of compute, because, you know, with our commercial model, the more compute that's required, the costlier the encode, and so we want to make that you know, barrier to entry for publishers lower, and we want to integrate more features. So there's lots of features to integrate from the VVC codec, and so that's really our focus over the next months and probably a couple of years. Just a little bit about how the cloud encoder works. It's a split and stitch mechanism. That means we get an input file from a publisher. We figure out how best to divide that input file into different segments, and then we send those segments off to different compute nodes in a distribution. Each of those compute nodes actually is doing the encoding. And so usually we split it up based on rendition and segment. The segments are sized based on scenes, so we try to detect scene and figure out you know, what's an ideal segment, not too long, not too short, and something that doesn't cross scene boundaries, and we do that to optimize for quality. And so now zooming in a little bit on an individual job. So this is one of those segments that was shipped to an instance in the cloud to be encoded. First you have to decode the input, then you scale it for the target resolution. You apply all your codec settings, do the encoding, mux it to a streaming output. I'll talk about that later in the session. And then stitch it all back together, put it into output storage on an origin. Now it's available for a user to stream. So I'm simplifying a lot of things here, but that's effectively how the split and stitch mechanism works. And so the encode part, right, we just replace it, in this case, with VVC codec. And this is a pretty normal way to do cloud-based encoding. Really, you have the core codec library. So in this case, we're using VVEnc from Fraunhofer for VVC codec, and then we have other codecs that you can choose from. But the process and the method to doing this encoding works the same way. You set a configuration, you push an input frame in, and you keep pushing frames in until the end, and then you pull encoded frames out and then concatenate them all together. So this is the part where we're contributing back to VVEnc, so the C-based interface to the library itself. And so initial results are it just works. So it's not a difficult codec to integrate. Again, we saw about a 40% bitrate reduction. Looking at subjective side-by-side tests, we think it's closer to even 50%. The convex hull complexity is simpler, meaning it's easier to predict the convex hull, or what are the ideal renditions that should be produced for adaptive bitrate streaming. And then prediction continuity, so this is again the OpenGOP previous frame reference approach that allows you to adjust resolution and bitrate within a given title. So that's really cool, and you can do that even for progressive outputs. So you can output an MP4 that is, and you can reduce bitrate. So imagine, you have, I don't know, maybe opening or ending credits in a title. You're not going to want to spend a lot of bits on those scenes. You don't have to, and that's what helps you to get more efficiency out of the encode. There are some limitations. So currently the memory utilization is quite high. It's okay, so it still works. We can get compute instances with lots of memory from all the public cloud providers, but we think we can tune that down. And then there's some limitations with segment durations. We have to keep the segments pretty short. This is from Fraunhofer, just a comparison of VVC to other codecs. And so I'll kind of translate this a little bit. The red lines, the two red lines, closer kind of bottom left, are two versions of VVEnc. So currently we're on version 1.8.0. This has improved, but not substantially. The blue lines are AV1, so it's the lines for open media codec. And then you have X265, which is effectively HEVC, as well as some reference encoders. And so what this means is, for different presets from slower to faster, by the way, VVEnc comes with those 5 presets, which are sort of defaults for to achieve a certain quality at a certain speed. And VVC performs quite well, right? As you can see, the closer you are to the bottom left, the better the quality, and the closer left you are, the better the speed. So initial results are very good. And then optimal bitrate ladders. So again, this was done in collaboration with Fraunhofer. In the first column, we're comparing the optimal bitrate ladder for VVEnc to the optimal bitrate ladder for HEVC. And when you do that, you get, again, the same expected result. About, depending on the measurement you use, 40 to 50% improvement in bitrate for the same quality. Now, when you compare VVEnc 1080p resolution to VVEnc optimal ladder, so think of it this way, 1080p resolution at maybe a lower bit rate, not the best bit rate. The difference is very small. And this is really interesting because what this means is that VVC is very good at using the minimum number of bits to produce a really high quality output. And when you do the same test for HEVC, the difference is quite high. So that means VVC is better than HEVC at spending fewer bits to get really crisp, high quality. And we actually have a blog post that I didn't put on here that was recently published, which shows you a visual representation of that. I think I'll stick that into the slides for you all to download later. But there's a very clear visual difference between HEVC and VVC for the same rendition. So I think that was pretty interesting. Cloud costs. So we talked. I already talked a little bit about this, but these are some specific numbers on cloud costs for given configuration. And again, VVC is 8 to 9 times more costly in terms of compute when you compare it to AVC, and about 4 times as costly to HEVC. I think that's the big takeaway. But of course, the bit rate is 40% of what it is for AVC. Excuse me. So what's next? We're working on a research paper for IBC. So I think it got accepted. So if you're heading to IBC or are interested in doing some follow-up research, look out for our paper. Again, that's going to be in collaboration with Fraunhofer. Our focus is really going to be on the OpenGOP referencing with RPR. We, just to recap, right, tools for video engineers, and to the gentleman's point earlier, it's only useful if we can provide some real value, and the real commercial value here is bitrate reduction, right? So we think we can do a lot more to optimize the codec for bitrate reduction with the OpenGOP approach. And just to recap, so right, closed GOP, that's how other codecs work today. That means every segment is decoded independently, right? So you don't know about any frames in a previous segment or a future segment, whereas with OpenGOP, you can reference those previous frames, which allow you to make those bitrate adjustments. And so we think that's the biggest benefit of VVC, and that's something that we hope to really squeeze more bits out of. So again, what's our expectation? Even incremental BD rate gain using this technology. Also, this is a basis for per scene or per shot encoding. So for basically, it's a way of doing content-aware encoding within a given title. We already support per title encoding, and that's benefited our customers substantially, and is one of the key features of the encoder. And while this is supportive for both VOD and live, I think our focus is going to be on VOD for now. There are some live implementations in the market already. You'll hear about one of them from Jan. And I think that's it.